invention of the electric engine and electric locomotive. At the very time when Watt was working on his steam engine, Fulton on his steam boat, and Stephenson on his locomotive, men were beginning to learn about a new power which has since become almost as useful as steam. That power is electricity. Electric engines are now employed in mills and factories to drive all kinds of machinery, and electric locomotives are used on many railroads to draw great trains. An electric engine includes two main parts: the dynamo, which produces or generates the electricity, and the motor, through which the electricity is converted into power. Before an electric engine could be constructed, it was necessary to discover a method of producing electricity in great quantities at small cost, or to invent the dynamo, and also to find a way to change, with small loss, electricity into power, or to invent the motor. Besides, a great deal had to be learned about electricity itself. The electric engine, like most inventions, is therefore not the work of one man, but of many men, working at different times and in different countries. The electric battery. Almost everybody knows a little about electricity. Very often, on a cold day, if one rubs his feet on a carpet and then touches another person, a crackling sound will be heard, and the person touched will receive a shock. Something like this happens when a cat's back is rubbed briskly. Despite these and other interesting things that have long been known, not much interest was taken in electricity, so that it was not until very recently that much was really understood about it. Men did not begin to study electricity with care until about 200 years before Washington became president. Otto von Guericke, a German, was one of the first to study it carefully. He made the first machine to generate or produce electricity. His machine was merely a globe of sulfur supported so that he could turn it by a crank. When he placed his dry hand on the moving globe, it would attract bits of paper like a magnet. A similar machine was made later by placing a glass disc so that it could be easily turned, and by fixing a number of rubber or silk brushes so that they would rub against the revolving glass. Alexander Volta, an Italian, was also a pioneer. He discovered in 1800 that two different metals in contact with each other would produce an electric current. From this discovery, he invented an electric battery. It consisted of a number of cups piled on top of each other. In each cup, he placed a disc of copper and a disc of zinc, covered with a brine of common table salt. The copper disc of the first cup was connected by a copper wire with the zinc disc of the second cup, and so on. A copper wire was also fastened to the copper disc of the first cup and one to the zinc disc of the last cup. On taking hold of these last two connecting wires, a strong electric shock was felt, and the current continued to flow regularly. A battery like Volta's can be made without the cups by using a glass jar. It should be remembered, however, that the strength of the battery does not depend upon the size, but upon the number of discs or plates. Volta's battery was the first easy way found to produce electricity in quantities. Years of study and experiment have shown also that the metals used by Volta, copper and zinc, are the very best to employ in batteries. The so-called dry battery, for example, used to work doorbells, was made until lately of copper and zinc discs covered with sand or sawdust, soaked in acid and sealed. The battery is today the most common of electrical appliances. There are one or two in almost every home. The magnetic magnet. Most boys at some time or other have owned a magnet, which, as you know, will pick up or attract bits of paper, pins, or even fillings. To make a compass, stroke a needle from end to end with one end of a magnet and float the needle on a bit of cork. Iron fillings arrange themselves in file like live soldiers if a magnet is placed under a sheet of paper and the fillings are spilled over the paper. It is the invisible currents of magnetism flowing around the magnet that make the fillings squirm about. For many hundreds of years, bar and horseshoe magnets were made by rubbing small iron bars over a natural magnet or lodestone. Lodestones are pieces of hard black rock found in Asia Minor, China, and Japan. They were thought to confer peculiar powers upon the persons possessing them. Such persons could win friendship, succeed in business, tell whether they were being married for love or for money, and were safe from many diseases. Naturally enough, magnets were looked upon as valuable possessions. Yet no practical use was made of them until about the middle of the 12th century, when a wise sailor placed a magnetized needle upon a float to learn which way was north. Magnets are now used for many purposes, and it was the study of them and their action that led to the invention of the dynamo, the telegraph, the telephone, and many other modern conveniences. The electromagnet. Sailors long ago noticed that when there was constant lightning, the needle of a compass danced about in all sorts of ways. The same dancing about of the needle was observed when a magnet was brought near a compass. These and other facts, like knives being made into magnets when a house was struck by lightning, aroused curiosity among scientists to find out what connection there was between magnetism and electricity. In the winter of 1820, it occurred to Professor Ørsted of Copenhagen to try a new way to find the answer. On a table before him lay a compass, and beside it was one of Volta's batteries. He connected the wires to complete the circuit of the battery, and brought one wire close to the side of the compass parallel to the needle. The needle swung around, just as if he had a magnet in his hand. When the current was sent through the wire toward the north, the needle moved to the left. When the current was sent through the wire toward the south, the needle swung to the right. Ørsted saw he had made a discovery. Passing an electric current through a wire makes a magnet of the wire. Magnetism, he said, is but electricity in motion. Ørsted's discovery was of importance, for it led to the invention of the electromagnet, one of the most useful of electrical inventions. The first electromagnet was made by Sturgeon, an Englishman. He took a round bar of very soft iron and bent it in the shape of a horseshoe. Around this he wrapped a wire, and through the wire he passed an electric current. He varnished the core, as the iron bar is called, to keep the electricity from flowing off or away from it. Sturgeon was surprised at the way the electromagnet worked. It was very much stronger than a natural or permanent magnet of the same size. But the most surprising element was that the instant the current was turned on, the iron core became a magnet. And when the current was turned off, the core practically ceased to be a magnet. It might be thought that this peculiar action of the electromagnet would make it a useless plaything. But it is this very action which makes it so useful. If a needle or other object is picked up with a permanent magnet, the only way to get it off the magnet is to scrape or pull it off. But to get it off an electromagnet, it is necessary only to break the electric current. The electromagnet is thus under our control. To put it to work, we turn on the electric current. To make it stop working, we turn off the current. You do this every time you push the button of an electric doorbell. We can control also the power of the electromagnet, that is, the size of the load it will lift. The man who taught us how to do this was Joseph Henry, an American. Instead of varnishing the iron core as Sturgeon had to keep the electricity from flowing off or to insulate it, Henry insulated the copper wire by covering it with a wrapping of silk. Instead of putting a single turn of wire round the iron core, he put many turns. On his first electromagnet, he put 35 feet of wire, making about 400 turns. These additional turns increased the strength of the magnet very much. Henry found that the magnet was stronger when wound with a number of separate coils of wire, the ends of each coil being connected with the battery. With a small battery, one of Henry's electromagnets lifted 85 pounds, and in 1831, he exhibited a magnet which lifted 3,600 pounds. Thus, by using a small or large battery, small or large iron cores, a few or many coils of wire, electromagnets of different strength can be made. Henry was also the first to make the electromagnet do work at a distance and to show us how it could be made useful. In telling of this, he says, "I arranged around one of the upper rooms in the Albany Academy a wire more than a mile in length, through which I was enabled to make signals by sounding a bell." This first electric bell was made up of a permanent magnet about 10 inches long, supported on a pivot and placed with one end between the two poles of an electromagnet. When the current was passed through the electromagnet, this caused the bar magnet to swing and strike the bell. Small electromagnets by the millions are now in use. In connection with the electric battery, they ring our doorbells, sound alarms, move signals, and the like. Enormous lifting magnets are now employed to handle iron and steel. Some of these will lift as much as 100,000 pounds. Electromagnets are thus of themselves doing all kinds of work for us, and in addition, they are, as we shall see, an essential part of the telegraph, the telephone, and the dynamo. The first dynamo. The discovery that an electric current would produce a magnet suggested to Michael Faraday of the Royal Institution at London the question, will a magnet produce an electric current? He kept asking himself this question over and over again. Oersted had changed electricity into magnetism. Faraday set about doing the opposite, change magnetism into electricity. He first tried to do this in 1822, but failed. He also failed in 3 other attempts. In the year 1831, he took up the problem for the 5th time. He coiled 220 feet of wire around a pasteboard tube and connected the ends of the coil to an instrument which would show if there was an electric current flowing. Taking a round bar magnet 8.5 inches long and 3/4 of an inch in diameter, he thrust it quickly full length into the coil. The needle of the instrument showed there was a current, but the current stopped when the magnet came to rest. He jerked the magnet out, and again the needle moved, but in the opposite direction. The needle swung back and forth each time the magnet was thrust in and out, but there was no movement when the magnet was still. Faraday at last, after 5 attempts, succeeded in producing an electric current from a magnet. He saw why he had failed before. In his early attempts, the coil of the wire and the magnet were left at rest. A magnet might lie in or by a coil of wire for 100 years, and no electric current would come from it. The electric current, as Faraday had learned, is produced by the magnet when in motion, or when the wire coil breaks through the currents of magnetism coming from the magnet. Faraday now saw how to make a new machine to generate electricity. A copper disc 12 inches in diameter and 1/5 of an inch thick was fastened on a brass axle. This was so mounted that the disc could be turned rapidly. A powerful permanent horseshoe magnet was placed so that the disc revolved between its 2 ends. A metal collector was held against the edge of the disc, and a second collector was fastened to the axle. Faraday turned the disc, and a steady current of electricity was produced. This was the first dynamo ever made. By persevering until he found out how to produce an electric current from a magnet, Faraday blazed the way for some wonderful inventions. Without the dynamo to generate the electricity, we should not have electric lights, electric streetcars, electric railroads, or electric-driven machines in factories. Making the dynamo useful. There are 2 parts to every dynamo, the magnet and the whirling disc. The electricity is produced by the disc, called the armature, breaking through or across the currents of magnetism coming from the magnet. The currents of magnetism in Faraday's dynamo were supplied by a permanent magnet, but the electromagnet supplies a more powerful magnetic field than the strongest permanent magnet. Therefore, in all the dynamos of today, electromagnets are employed. In the very largest dynamos, there are a number of these, each more powerful than the strongest one made by Henry. The armature in Faraday's dynamo was merely a copper disc. Present-day armatures are made up of a core or inner portion, and the windings of copper wire over the core. The core in the common armature is made up of a great number of very thin, soft sheet iron discs. Around these are wound many thousand turns of copper wire. Between the time when Faraday made the first dynamo and the present, many men worked to make the dynamo useful, that is, to make one which would produce electricity in large quantities at a small cost. Among these experiments are to be counted Siemens of Germany and Edison of America. Under the careful and patient work of these and other men, the simple dynamo of Faraday grew into the monsters of today. From these monster dynamos, hidden away in some remote powerhouse, comes the electric current to light our homes and streets, to drive the machines of mills and factories, to propel streetcars, to haul passenger trains, and even to cook our food. Finding the motor. What was now needed was a machine, a motor, that would convert electricity into power, which could be used to turn all kinds of machines. Toy motors were made as early as 1826, but a practical motor, even if a good one had been invented, was not possible until the dynamo had been perfected and cheap electricity was to be had. In 1873, there was an industrial exhibition at Vienna, Austria, where a number of dynamos were displayed. One day, an absent-minded workman connected the wires of a dynamo which was running to one that was standing still. To his surprise, the armature began to spin around. It was thus discovered by accident that the dynamo, invented to produce electricity, could be used also to change electricity into power, or that the dynamo is also a motor. Dynamos and motors are now built almost alike, but motors do not have to be as large and heavy as dynamos. It thus came about that the men who perfected the dynamo at the same time, without knowing it, perfected the motor. The dynamo and motor at work. The motor was immediately put to work. At the Industrial Exposition at Berlin in 1879, Dr. Siemens exhibited a small electric locomotive, drawing a train of 3 small cars. The track, about 1,000 feet long, was circular, and for this reason was the first electric railway and called Siemens Electrical Merry-Go-Round. In 1881, Dr. Siemens built a streetcar line 1.5 miles long. A motor was fastened between the axles of an old horse car, and a dynamo exactly like the motor on the car was set up to furnish the electricity. The new electric line easily drove the omnibus from the street. Electric street railways were soon being operated in all parts of the civilized world, and no sight today is more familiar than the trolley car. Edison was quick to see the practical importance of the motor, and on hearing of Dr. Siemens' electrical merry-go-round, set to work. His first electric locomotive was built early in 1880. It was made up of an ordinary flat dump car, on which was mounted a dynamo for a motor, known as a long-waisted Mary Ann. Improvements quickly followed, and it was not many months before his motors were ready to propel streetcars. The first electric street railway in America was built at Baltimore in 1885. Edison was also among the first to see that electric locomotives could be built large enough to draw freight and passenger trains, and by 1882 he had a big electric locomotive on exposition at Menlo Park. Considerable use is now made of electric locomotives for hauling trains in and out of large cities, and on a few railroads they have taken the place of steam locomotives, either altogether or in part. Besides being employed to propel trolley cars and locomotives, a great many motors are being used in mills and factories to drive machinery. But it must not be supposed that all motors are large and powerful. They are of almost every imaginable size, from the great monsters in electric locomotives down to the little motor that is just strong enough to run a sewing machine, or whirl an electric fan, or propel a toy engine.